In part 3 of section 18, I want to briefly talk about the idea of transformations of exponential functions. We're not going to have an overwhelmingly large number of examples here. In fact, I just want to do one example with this. We've already talked about the transformation concept as it applies to your squaring function, identity function, the square root function, all the parent functions that we've had so far. And then we even talked about it when we did the reciprocal function and the reciprocal squaring function. It's the same concepts, just applying to a new shape. That's really all it is. There are 3 transformations that I want you to be familiar with as it applies to the exponential function. That's going to be the vertical stretch and shrink. Now, included with this, I'm going to say, and the reflection that is going to be coming from the same place as the vertical stretch and shrink, and that's going to be the reflection over the x-axis. For 2 and 3, I have the horizontal shifting and vertical shifting. So those are things that we are very familiar with. Now, definition 18.3 is going to describe for us what we call the transformation form of the exponential function. So it's going to be an adaptation of the y equals b to the x, so that way it accounts for stretching and shrinking vertically, reflection over the x-axis, horizontal shift and vertical shift. So what you'll notice in comparison with your basic y equals b to the x is that you have a, you have h, and then you also have k. Now the h, it says x minus h. That would be the same as what we saw with other functions as representative of the horizontal shift. The plus k would be the same thing that we saw in other functions for the vertical shift. So there's nothing new to learn here in terms of transformations. We just have to understand where they get applied with this function. And then for part A, that is going to, or for the letter A, not part A, the letter A here, that's a multiplier. And that multiplier is going to do one of 2 things. It's either going to create a reflection if it's a negative value, or it's going to give us a vertical stretch or shrink. And I want to take a look at example 18.7 for an opportunity to be able to practice this. We have here the function g, which has a domain of all real numbers, given by the equation g of x equals 3 raised to the x plus 2 minus 3. One of the things that's worth mentioning about the structure of the equation is that there is an implied parenthesis around the 3 as it's being raised to the x plus 2. And the reason why I want to mention that is because that also means that there's an implied multiplier of 1 right there. So when it comes to trying to identify your a, your h, and your k for transformation purposes, it's good to be able to see all these little components. That means that your a is equal to 1, your h is going to be coming here from the x plus 2, and then your k is coming from the minus 3 that's there. Now, your a is telling you specifically that there is no stretching or shrinking, and there's also no reflecting going on. The h, because it says x plus 2, tells us that we have to do a shift to the left by 2. And then for the k, since it says minus 3, this implies that we are going to need to shift down by 3. So I want to look at the parent function for this, and the parent function for this would be the equation y equals 3 raised to the x. This is the parent function. If I take away the plus 2 and the minus 3, this is what I would be left with, just y equals 3 to the x. So we got to see y equals 3 to the x on example 18.6. So I'm going to go ahead and graph it so we can see it again here. And I can get away with just using 2 points on this, 0, 1, and then the point at 1, 3. And I can get away with that because I know that exponential growth has a very particular shape to it. There's a horizontal asymptote, and there is also going to be an increase to the graph. So it's going to look something like this. You don't have to have 5, 6, 7 points to graph these things correctly. You only need really 2 points, maybe 3 points, if you understand what the shape is supposed to be. Now let's take this picture and let's shift it. So we're going to shift it to the left by 2 and down by 3. So I'm going to take the horizontal asymptote and shift it down by 3. And then I'll take my 2 points and shift them down 3 and left 2. And then I'll draw my exponential growth. And that becomes the graph of g. And that first picture I'm going to label as y equals 3 to the x, because that was just the parent function. The only other items to do, state the domain. So when we apply the shifting, it doesn't have any effect on the domain. The domain is still going to be all real numbers. But it does have a little bit of an effect on the range, because it moves the horizontal asymptote with that shift down. So the range of g is now going to be from -3 to infinity. And it also changes where we have our asymptote. The horizontal asymptote now has the equation y equals -3.